Good morning, everybody. Welcome to the second webinar of a series of 3 in the frame of the NuReDrain project. My name is Charlotte. I am the project coordinator and I will be moderating the webinar of today. We will talk about the project results related to phosphorus recovery and phosphorus removal modeling. And before I give the floor to the speakers, I just want to highlight some practical issues with you. And I try to go to the next slide. Okay, that worked, sorry. So I want to ask to all people who attend to mute yourself. If you have a question during the presentations, you can put them in the chat. And after each presentation, there will be a Q&A session. I will be reading these questions out loud, or you can also unmute yourself if you want to ask your question directly to the speakers. This webinar is recorded, and after the webinar, we will send you the handouts and also the video. It will be put on the NuReDrain websites. So as a brief introduction for the people who are new today, the NuReDrain project is about nutrient removal and recovery from drainage water. It's a project which is funded by the Interreg North Sea Region program, and we are 11 partners working together from 3 different countries, being Denmark, Germany, and Belgium. So the goal of our project is to combat eutrophication, and we do so by installing end-of-pipe technologies to remove nitrogen and phosphorus from agricultural-related waters before they end up in the surface water. We hope to have technologies that in the end can remove 50% of nitrogen, 70% of phosphorus. From the adsorbed saturated phosphorus, we want to be able to reuse minimum 20%. And at the end of the project, we hope that 40 organizations will be adopting our solutions. So we mainly focus on drainage water, but we also look to greenhouse effluent, to surface water, and to a water reservoir for drinking water production. So the project has 6 different field cases spread over the 3 different countries. And we don't only look to technologies to remove the nutrients, but we also focus on experiments to try to recover the phosphorus. And there is also a work package on modeling in which we try to see how a bigger catchment would, how the results of one filter and multiple filters could, sorry, I will recap, what the nutrient removal potential would be if we would install the filters over a larger surface area. Okay, with that, I did a small introduction and I now want to give the floor to Els. So I will stop sharing my screen and Els will share hers to start her presentation.
So can you all see the presentation?
Not yet. We see you, but the presentation is not there yet. Yes, it's there.
Okay. Dear all, my name is indeed Els Pauwels and I'm working at the Ornamental Plant Research, PCS, in Belgium. And the first webinar today is about the reuse of saturated filter materials as fertilizers for ornamentals and vegetables, in fact, agriculture crops. So as Charlotte already showed, and we saw in previous webinars that within the NuReDrain project, we have filters. We have filters for N, we have filters for P, and for the P filters, you can see one here at the picture. I hope it appears. No, it doesn't appear. But we have filters, for instance, at forestries, where we have big P filters with 1 cubic meter of material in it. And at a certain moment, these materials are saturated. And of course, we wonder what can we recover, can we reuse this material as a P fertilizer? Well, the KU Leuven tested several materials that seem to be interesting material for our purpose, namely their value of adsorption and desorption of P. You can see here at the picture of the lab test that they made, and after the first screening, ICS, diapure, redmedite, baselite, lidonite, phyto A and B, LDH, and ferrosorb were remained for further testing. But of all lab test materials, it was the ICS grains that was one of the best materials in adsorption capacity, although there were other materials as diapure that were also very promising. But why did we then choose for the ICS grains, the material of which we talked already in a lot of other webinars? Well, first of all, ICS, iron-coated sand, is in fact a waste product from the drinking water production. So drinking water production companies, they have to get rid of the iron of the water that they pump. And how do they do that? They use sand filters. So sand grains capture, adsorb the iron. When the iron is saturated, when the grains are saturated with iron, then this is idle material for us to use to remove the P. And we at PCS, we had already positive results obtained in another previous project subsidized by Vlagua Vito, and that was called FOSCAP. And in this project, it was already shown that ICS give a very good removal of P-rich drainage waters. It can handle also a high conductivity of the filters, but this is depending on the size of the particles of the ICS. Until now, it's sufficiently available and relatively cheap, but of course, this can change in the future. That really depends on the market. So maybe the question raised by you now, how soon and when are these materials in fact saturated? Well, we must say that the saturation of the grains is slower than we first expected. It seems that they can absorb more P than we thought. But why that is, Nico, the next speaker, will tell you more about it. And then the next question was then, if the grains are saturated, what can we do with them? We have all this P adsorbed on the grains. Can we reuse it? Or is that not possible? And we knew already that the pH would play a very important role. So we thought, well, let's keep it simple. We just take a plant with which can grow, for instance, by a very low pH. And that in Belgium, it's pretty, for us, it's simple. Just we take azalea that we can grow at low pHs. What does that mean? That our pHs from 4, 5, 5.5, certainly not higher. But it isn't possible, of course, to grow plants at pHs of 1, 2, or 3, certainly not ornamentals. So the lowest was azalea. We had some treatments. The first treatment was just a normal treatment, just normal P, normal N. And then we had a treatment where we gave no P at all externally, just mixed 30% of the ICS into the substrate. So we hoped that the P would come from the ICS grains without any treatment of the ICS. Unfortunately, there was almost no natural desorption of the P. We saw a little desorption of N, which was surprisingly, but that was what was remarked, but no desorption of the P. And the plants that grew with ICS, they were of lower quality compared to the control due to really a P shortage. So at low pH from 4, 5, 5.5, it didn't desorb. Then the next year, we thought we'd take other plants that can grow at higher pHs. Maybe that's the clue, but also, of course, higher pHs. That doesn't mean pHs of 12 or 13 or 14, that's just pHs of 7, maybe we go to 8. There are plants that can grow by 9, but certainly not higher. So we used Buxus, lavendel, and Hydra in our next trial. And of course, we had again the treatment where we gave just the standard N and the standard P. Then the second treatment, we gave no P at all, only N. And the third treatment was standard N without P, but also again 30% of the ICS granules mixed into the substrate. The result was a bit similar as last year. The growth for the treatment 1, the standard N and the standard P, remained the best. Of course, treatment 2 without P at all, plants were really smaller, but also to the plants of treatment 3, where we added 30% of granules, were also smaller. On the plants itself, at that moment, we saw no phytotoxicity effects of adding the ICS grains. We did a lot of analyses, which I will not show here, but I just must say that it was for the substrate analysis, it was very difficult to do them because it was not easy to remove. It is really very difficult to remove the ICS grains for analysis out of the substrate because sometimes they are so small. Here you see an overview of the trial. This was the setup. At the beginning of the trial, the 3 plants, and this was more at the end of the trial where plants were flowering or at the end could be harvested or sold. So the next step was how can we, it doesn't desorb from natural way from the ICS grains, it's just too good material to adsorb the P, and maybe therefore it's so difficult to desorb it. There exist phosphor-soluble bacteria or phosphor-soluble microorganisms that maybe can help us doing the desorption for us. You have inorganic phosphor and organic phosphor, so it wasn't the same to which PSB we would use, but companies helped us to choose the right ones. And we did another trial then the next year, and we chose therefore Hydra. You see here the setup, and we also, as you can see here, the lysimeters, we collected the drain water and we analyzed also the drain water of the different treatments. So the different treatments were then, of course, again, the normal N and normal P, the normal N without P at all, the normal N without P, but added with the 30% granules. And then we had some doses or different PSBs of PSMs, phosphor-soluble microorganisms that we added. So we hope they would help to release the P. You see here at the beginning, the ICS grains mixed into the substrate, and this is a photo rather at the end of the trial. But again, unfortunately, we're not lucky. We have the standard N and standard P. This is the fresh weight. So you see clearly that they are the best plants with just the normal N and normal P. Of course, without P, plants were a lot smaller. Adding the 30% ICS gave an improvement, which was rather significant, but not high enough. And adding the PSBs sometimes even gave worse results. There was some reaction, I think. We don't know quite well why, but anyway, it didn't reveal what we wanted. It didn't help the bacteria what we wanted to have. Also, our colleagues in Inagro, they did some trials to check these results. They did 2 trials on endive. They did a growth chamber experiment and a spot experiment, and they did a trial on maize. They used in the 3 experiments the ICS also as P fertilizer. They also added the PSBs to help to release the P. And they used commercial or already commercial products for these trials. So here you see the maize trial. First, plants were inside. Later on, they were put outside. You have, of course, the control. Then 2 references, in fact, where just polyphosphate and superphosphate was given. And then the different PSBs, whether with ICS or just with the control, triple superphosphate added or nothing added. But also in all trials of them, the fertilization treatments with the references they gave really the highest yield and the best results, and they didn't see really positive effects of the use of the PSBs in combination with the ICS. So there was no indication that the ICS was here a potential as P fertilizer. So we had to look at other possibilities since it's so difficult to desorb the P. It is possible, but that in a chemical way, and that Nico will tell more about it in the next webinar. But just we looked further at other possibilities to use the ICS. We were wondering, why shouldn't it work maybe against slugs? Since if you look at authorized products right now, then you will see that Iron Max Pro, slugs, Derex is certainly in ornamentals authorized against slugs, and they also contain iron phosphate. But so we wanted to test it, but unfortunately we had in Belgium 2 very hot and dry summers, so we didn't see any slugs at all on our plant, so we couldn't test this. So that is something still we have to check. What did we do also? We tested 14 different plant species. They are all listed up here. And we just added 30% of the ICS into the substrate and compared with the control. And we just gave the normal fertilization. So there was no given less P or something, no, just the normal fertilization was given, just to look at them, whether we see phytotoxicity reactions or not. And I must say, on the most of the plants, we saw that they were sometimes smaller and more yellowishing, so less dark. And when we did analysis, then we saw that really the ICS grains were, we thought they were saturated, but they were not completely saturated. And they even took out the P from that was in the substrate. They absorbed that P too, so it was less available for the plant. That was for the most plant species. We didn't see this effect on chrysanthemum, and we didn't see it on petunia, Surfinia. On the other plants, we saw a rather negative effect. Another trial we did was with Chlorophytum. Also there, we mixed 30% of ICS and the control. And at the end, we saw no differences at all. Even with ICS, we had a higher fresh weight of the plants. You can see it yourself here. At the left, you have the plants without ICS. At the right, you have the plants with ICS. And you see that they are certainly not smaller or less good. They seemed even a little bit better. So we had 3 exceptions where we didn't have the phytotoxicity effect. We had Chlorophytum, Chrysanthemum, and Petunia. And therefore, now in 2020, we have an ongoing experiment of 20 plants per treatment on Chrysanthemum to test whether what we saw, it was just coincidence or it is really something we can believe in. Here at the left, you have the control, so the normal substrate that we always use for Chrysanthemum. Then we added 30% of ICS grains in this treatment, and we added also 30% of pellets. So you have the grains in the drinking water companies, but in the sand filter they also have sludge, and a lot of sludge, in fact. And from that sludge they can make pellets. Of course, that's an extra step to make the pellets. But we have already, I think, for many years, also a filter filled with pellets at PCS, and it works certainly as well as the grains. So therefore, we used also saturated pellets into the substrate, and we mixed also 30% of them. And then you see here an overview of the trial. I think some weeks ago I took the picture, and I see no difference at all in growth between the different treatments. So they look all the same. We didn't do any measurements yet, but visually they look really the same. And this is a picture I took yesterday, and we have already some flowering, but that's really also the same in all treatments. Even the control, it seems a little bit smaller, but that's just visually. The measurements will still be done. Then also what we saw in the trial, for instance, certainly in 2018, but also in other trials, is that where ICS grains are mixed into the substrate, we have less liverwort. What's liverwort? You see here the pictures of it. It's something very annoying. Really, growers don't like it to have it on the pots. They have to remove it manually, and it comes back very easily. So it's something to avoid. So it would be good if ICS can help to avoid these liverwort. We also did a test on camellia, and you can see here where the ICS was added that there was less thallus and there were less umbrella-like reproductive structures of liverwort. What do I mean with that? These are these reproductive structures. So that can be also a plus. So we thought, yeah, we can maybe use it as cover material. Also a very important thing for in ornamentals, certainly in nursery stock. And therefore in 2020, we set up a trial with rhododendron in which we have different cover materials where we test. And ICS is one of the cover materials that is used. Now we are counting the weeds and looking at the liverwort, the presence of it, but also this trial is still ongoing, and with the rain now it will be more interesting to follow the further this trial. It's not only on rhododendron that we have the trial, we also used Azalea japonica to perform the trial. But here I don't have results yet. So that's the end of my talk. I don't know if people have any questions.
Yes, thank you, Els. There are 2 questions in the chat now. The first question is, how much P is in the 30% ICS treatment? And is that amount comparable to the triple superphosphate dose?
So the amount was comparable indeed of the triple superphosphate, because it was counted in that way to give us the same amount of P. Also for the reference, it was the same amount. And it depends, but I think Nico knows even better how much P can be absorbed at the ICS grains, but at PCS it's sometimes even 60 milligrams per kilogram, I think. Nico, can you?
Yes, the maximum that we measured is about 1.5 mass percentage. So 1.5% of the mass is P. And for the ICS, the granule contains about 60% of iron, and the rest is sand, silica.
Mm-hmm. So, but in milligrams, I have numbers of 60 milligrams, I think, something like that per kilogram.
Per kilogram, you say? It can be much more. It can be much more.
Yeah.
Yeah, that's actually the second question. What is the amount of P per kilogram of ICS? And what is then the P over iron ratio?
Yeah, dus that's what I said. 1.5% of the mass is P.
Yeah, yeah.
So then with that number, you can calculate how much ICS you have to add to your plants.
Yeah, okay.
So, and this was all calculated before the startup to have the same amounts of P into the substrate as a
The
start.
problem here is the availability of the P. You will see my presentation. You need higher pHs to desorb all the P or a great amount of the P.
Yeah, and that's the whole problem. Growing plants, like I said in the beginning, can range from pH 4 maybe till pH 9. Chlorophytum is one of the plants that is known that can support very high pHs, but really the maximum it can support somewhere 10 maybe, but yeah, that's not 12 or not 14. I don't know any plants yet here grown in Belgium or in the North Sea region that can support very, very low pHs and very, very high pHs.
Yeah, okay, thank you. Does anybody else has a question for Els? It seems not. If so, we can continue the webinar and give the floor to Nico. Els, you can stop sharing your screen, and then Nico can start with his presentation, which will go further onto the P recovery.
Is it okay like this?
Yeah, we
for
see
everybody?
it. Yeah.
Hello, I will introduce myself. I'm Nico Lambert from the University of Leuven, Belgium. In the upcoming 20 minutes, I will introduce you in the work we performed on the recovery of phosphorus from adsorbing filter materials. But here we will talk about the chemical treatment as an alternative of the direct use of the granules as a fertilizer. So what we already know and mentioned today, that is the water flows from agriculture contains an amount of N and P from unused fertilizers. This effluent water can be drainage water from tile drained fields, or can also be effluent water from greenhouse effluent. Yeah, the latter is often higher in concentration than the drainage water from tile drained fields. So for both nitrogen and phosphorus, we are searching for alternatives to capture this nitrogen and phosphorus from the effluent waters. Our proposed solution is the adsorption technology using aluminum and iron-based P filter adsorbing materials. Last year, we are focusing on 3 adsorbing materials: iron-coated sand, as Els mentioned. It's a waste product from the drinking water companies, but also new materials that are still in the research, but they are doing well. Vito A and B, these are two new materials, and also Diapure as the third one that we will research now, but also in the future. So there is one relevant research question. What about the saturated adsorbing material? Should we simply dispose this material as a solid waste? The answer is no. No. But when is it necessary to recover or regenerate the materials? So it's our intention to integrate the whole process in a circular process so that we can reuse the material, but also to recover the phosphorus from the material. So the main objective of the research that I will present you today is to find the right strategy for regeneration of the saturated sorbent and also the recovery of the phosphorus that has been adsorbed on the material. So we will try to do that by making use of different cycles of adsorption and desorption. And afterwards, the desorbed phosphorus, we can then recover it by precipitate it or used directly with the irrigation water as a fertilizer. So two main objectives, the regeneration of the saturated sorbent, but also the recovery of the phosphorus. The reusability of the granules is as important as the recovering of the phosphate from the material. That has to that's the result of the fact that that the material itself is has an economic value because you can speak of about 500 to 1,000 euros per ton of material. It can be even higher if you count in the transportation cost from the facility to the greenhouse, for instance. In the literature, different desorption reagents are already tested. So we have inorganic and organic acids. We will not focus on that one. I will explain later on in the presentation. Chelating agents, but for us the alkaline solutions are the most important, but they are all already tested in literature, but not on these materials, of course. So we propose a desorption process using alkaline solutions, and it's our intention to not harm the granules itself so that they can be reused. Okay, some theoretical basis. We know that the initial pH of the water itself has an important influence on the adsorption capacity of the iron-coated sand. And in this example, I will focus on the iron-coated sand, but we do also experiments on the other materials. And we also know that adsorption and desorption are balancing processes and until an equilibrium is reached. And this has all to do with the pH of the water itself. So we did a test and we exposed some ICS granules to different pHs from 1 to 14. And we got this graph. Can you see my pointer? No?
Yes, we can see
okay.
it.
Okay, that's important. If we look at the pHs for the adsorption, usually the drainage water has a pH between, let us say, it's the minimum and maximum 6 and 8. So you can see that we have here a very good adsorption capacity, which you can read from the y-axis, of about 6 to 10 milligrams phosphorus per gram of sorbent, dry solids, and the sorbent is dried. So 6 to 8 milligrams of P per gram. That's a number that you can remember for the rest of the presentation. This is the window in which we operate for the adsorption. If we want to desorb, we are looking at the higher pHs, and then you see the adsorption capacity here. It's much lesser than it's less than in the frame of pH 6 to 8. This means desorption can take place. We saw at a pH of 13 maximum adsorption capacities of about 1 to 2 milligrams per gram of sorbent. This means all the rest can be desorbed from the granule. There is one important pH, and we call it the point of zero charge, and I've marked it on the graph. This is this pH, 8.7, and this means at this pH the charge on the surface of the granule, let us say, is 0, and it means all pHs above the 8.7 are okay for desorbing, and all the pHs that are less than 8.7 then adsorption can take place. For us, we would say a pH of more than 11 is okay because there you see a steep drop of the adsorption capacity. Okay, a little bit chemistry on the surface of the granule. You can look at this side of the figure. So I said at the point of zero charge, and it's this pH, we have a charge of 0. But at higher pHs, we have a negatively charged surface. This means that there is repulsion between the surface and the phosphate ions, which are also negatively charged. There is a repulsion, but there is also a competition between the phosphate and the hydroxyl ions for the same adsorption places on the sorbent. So what we know now is at pHs above 8.7, you will see a decreased adsorption capacity, and this means desorption is possible. So we were looking at pHs higher than 8.7 in our research. So this brings us to the concept of add and desorption. We did a lot of column testing. In lab, these columns are very small, let us say. Els showed us a picture of our column setup in the lab. As you can see, the phosphorus is fed in an upflow manner. And after a while, the whole adsorption material is saturated, and some phosphorus will end up in the effluent of the column. I have a graph here, and what you can see on the graph is, in function of time, you see the ratio between the effluent concentration, and the concentration of phosphorus at the top of the column, the ratio of this concentration to the ratio to the concentration in the influent. This means after a while, this ratio will go up until it reaches a percentage of 10% in this case. After a while, you see all the phosphorus will end up in the effluent, and at day 300, you see here the filter is fully saturated, and this is the moment you could say to regenerate. But this is also too late. If the concentration is too high, you have to do it like here after 180 days. Then you have a low concentration, still a low concentration in the filter, and you can desorb all the phosphorus from the filter. How we do it? In the lab, we are using sodium hydroxide, and we pump it over the filter system, and you see after a while all the phosphorus, or a great part of the adsorbed phosphorus, is desorbed and end up in the solution. That solution we can then use directly as a fertilizer, but we can also do a precipitation like with calcium hydroxide, or in another way, to make a fertilizer again. That's the concept that we are using. So after a while, we will desorb the filter material. Then we can restart adsorbing, and at day 350 we desorb again, and so on, and we call it an intermittent regeneration of the ICS. That's our goal. So let us look at the materials and methods. We did a certain amount of batch desorption experiments in the first phase of our research. Afterwards, some continuous filter desorption experiments, and we analyzed the liquids, but also the granules. In our batch tests, we always used 5 grams of pre-dried saturated ICS, and it was brought in contact with a sodium hydroxide solution. We had some variables. Of course, the sodium hydroxide concentration from a moderate pH, let us say, to a pH of 14, which is a very high pH, of course. We varied also the desorption time from 5 minutes to 48 hours. And we varied also the solid liquid ratio between the solid are the granules. The liquid is then the sodium hydroxide that we used during the desorption batch experiments. In a continuous filter desorption experiments, we used 1 liter of sodium hydroxide, and that solution was recirculated over the adsorption column, and these columns were filled with 128 grams of saturated ICS granules. So afterwards, we did all the analysis on ion chromatograph and ICP, but the solids were analyzed by an electron microscope with the option to see where the phosphorus is in the granule itself, and it's done by EDX. So now the results. I will start with the results of the batch experiments first, and that I explained already in the answer of the question from the first presentation of Els. We analyzed 1 gram of saturated ICS, and we could see that 1.5% of the mass of the ICS was phosphorus. And the most part of the granule contains, of course, iron. It's about 60% of the granule. Good. The results of the batch tests. We have the first figure here, this one. And in this first figure, we can see, and we see on the x-axis, we see the desorption time, and then how much phosphorus is desorbed from 1 gram of dry solids. What you can conclude from this figure is, yeah, you need certainly 24 hours, maybe even 38 hours to desorb a great part of the phosphorus from the granules. What you also can see is how when the concentration of the sodium hydroxide is higher, yeah, then you can see that there is more desorbed phosphorus from the granules. So with this in mind, we did a second experiment, and in the second experiment, we varied the solid and liquid ratio, and you can see from the second figure that we need a minimum solid liquid ratio of about 0.1 grams of granules per milliliter of sodium hydroxide. That's recommended, that you can see from this figure. Somewhere here I say everything what is higher is better, and so we can desorb, like, let us say 6, 7 until 8 milligrams of phosphorus from 1 gram of dry solids. Good. With this knowledge, we did some column experiments, and these columns are scaled down from bigger columns that we tested in the field. As already mentioned, the columns contains 128 grams of the granules, and then we started with different sodium hydroxide concentrations to see what is the effect of the concentration of the sodium hydroxide. So as you can see in figure 3, we have on the x-axis we have the desorption time, and on the y-axis again the desorption capacity, how much P that can be released or desorbed from the granule. As you can see on the figure, the concentration of 1 molar of sodium hydroxide, that's about a pH of 14, almost 14 when we did the control, and the concentration of 0.5 give good results. The results of the concentration of 0.1 was too low. I've zoomed in on the first hour, the first hour of the experiment, and so you can see here the 0.1 molar concentration. We don't have any spectacular desorption, as you can see. For the other ones, the 0.5 and 1 molar, we had good results. You can compare it with the maximum desorption capacity that we realized in the batch test, and then you can see, yes, the maximum here is 5 to 6 milligrams per gram of dry solids of the granule. Good. These were the continuous desorption experiments. Then we want to focus on the granules, the solid material itself. I show here some adsorption experiments that we did last year, and these are 2 different experiments with the same material. It's in both cases iron-coated sand that we analyzed. What is the difference between both adsorption experiments? The first one on the left side here, there we had a contact time, and we call it the empty bed contact time of 5.5 hours. That's a long contact time when you think that activated carbon filters have a contact time much more or less than we speak in terms of minutes, not hours. The second experiment, this one, at the contact time, empty bed contact time of 0.5, half an hour, let us say. And what is the difference? What we could see is in absorption, we are looking for the breakthrough of the filter. And let us say in the first experiment, we have a breakthrough at day 100, what is it? 80. And we say then we have to stop filtering and desorbing. We let the experiment go to the complete saturation of the filter, and at day 280 we took a sample of the granules, and these granules were analyzed by electron microscopy with EDX. Just the same with the second experiment with a short contact time. We had a breakthrough at, let us say, 7 days already. We let the experiment go on until fully saturation, and after 35 days we took a sample and we analyzed it with the electron microscope with EDX. The results are shown on the next slides. What you can see here is the results from the second experiment with the short contact time. What we do we embedded the granules in epoxy resin, an epoxy resin, and we polished it until we can see the granule core, so that we can take a picture with an electron microscope. And this is a normal microscope picture. This one is the picture of the electron microscope, and then we can see with the EDX where the phosphorus is adsorbed on the granule. And what you can see is in the center you have some phosphorus adsorbed, but the most part of the phosphorus is adsorbed at the surface, the outer surface of the granule. That was the conclusion that we took from these images. If we compare it with the granule that we took from the experiment where we had on 5.5 hours of contact time, a lot of contact time, then you can see this is the picture showing the sand core, this silicium, and all the rest is iron. And when we make an overlay of the phosphorus on this microscopic image, you can see that a great part of the phosphorus is adsorbed at the surface of the sand core. This means that the phosphorus can migrate to the towards the core of the granule, and this is only possible when the contact time is great enough, like some hours. Then we see this process happening, and this is also the reason else why the adsorption capacity can be much higher in columns with a high empty bed contact time. So there is something negative also when the phosphorus is at the core of the granule. Let us say, I think it's difficult to desorb this phosphorus from the granule itself. So with these images, we could say that we have some good conclusions to work with. So from the, I will conclude my presentation with this. I give you some general conclusions. I think the optimal sodium hydroxide concentration is 0.5 molar that we saw from the batch test, but also in the continuous experiments. We will need a contact time for desorption of about 24 hours or more. We managed to find the optimal solid-liquid ratio during the desorption, and it's somewhere between 0.05 and 0.1 grams of granule per milliliter of sodium hydroxide. From the experiments with the granules that we analyzed with a very long contact time, we could say we can realize a desorption efficiency of about 40% at a concentration of 0.5 of 1 molar of sodium hydroxide. I know these are very high pHs. Maybe we have to look at lower pHs and then see if we can get good results from it. But when the phosphorus is at the outer layer of the granule, at the surface of the granule, which we saw in the experiments with the short contact time, I suppose then we get higher desorption efficiencies also. What we saw, but I didn't mention during the presentation, that there after each desorption cycle, there is leaching of iron from the granule itself. It can be a problem, so we can regenerate 1, 2, 3, or 4 times, but not 10 or 20 times, I suppose. Desorption of P from the inner layers of the granule will be, I think, a problem. In the future, what to do next? Yes, we will investigate whether other adsorption materials are better suited for desorption. We know already from batch experiments that the Vito material and Diapure will be better to desorb the phosphorus from the material. We will also looking for ways to reduce this desorption pH. 13, 14 is high, I know. And also carrying out continuous long-term tests in which we will cycle between adsorption and desorption. It will be done in the coming months. So that was my presentation. Maybe there are questions. Certainly, there will be questions.
Yes, okay, thank you, Nico. There are indeed some questions. Perhaps first of all, to highlight that the Vito and Diapure materials, as explained by Nico, these are materials which are currently being developed also in the project and being tested in the field, so they are not yet commercially available. So that's why you might not find information about it in literature or on the website, but we work on it. Okay, so let's go to the questions, Nico. A question of Bernd is, how many pore volumes of the column were exchanged before the concentration, the ratio C0 is equal to 0.1, before that ratio was reached?
Okay, can you?
Yeah, how many pore volumes of the column were exchanged before your 0.1 ratio was reached?
How many cycles per? Okay, yeah. We don't count in that way. We only monitor how many days the column is active. But I can do it. I think if I know the pore volume of the materials, I can calculate it, but not now, of course, because I don't have all the information, but I can calculate it, I think.
Yeah, I know you have that information about the pore volume, so it might be something interesting to do.
Yeah. Because I mentioned the empty bed contact time. This is not the real contact time. The real contact time is much lesser because when you calculate a real contact time, you have to know the pore volume of your column. That's true.
Yeah. Okay. Then Els asked, so why do you already start with your desorption when your C to 0 ratio is still low? Why don't you do it when it's already a bit higher? So you show the graph. Huh?
Yeah. In fact, in our cases at 0.1, we exceeded already the limit, the standard limit of 0.1 milligrams P per liter. That's why we did it already then, so that we can manage a very low effluent concentration. That's the why.
Yeah. Okay.
Is it a good answer to your question, Els? Okay. Because otherwise, if you wait until complete saturation, yeah, then you have the influent concentration in your effluent, and that's
then your filter makes no sense anymore.
Anymore. We have to keep it low.
Yeah, that's true. Yeah. Okay. Then another question is, how much P was contained in the fresh ICS? So now you said, and there's 1.5 mass percentage on your dry material, but do you have an idea then on the fresh material?
The fresh material with no, that we use in the fresh material for our filter systems. That comes from the water company. Yes, I think that's, these vary. We have, but it's in a next publication in the coming months. We have the results from the different materials that we have from PITPA, from the different facilities, and then you can see there is a big difference in P content from the different locations. What we did is we selected two where the phosphorus concentration was very, very, very low. I don't know. I don't remember the numbers, but these were very low. And there was a higher concentration of from one facility. There was a higher concentration, and then there was 2 milligrams of phosphorus per gram of dry solid. This means this material was not selected by us as a filter material for PD adsorption.
Yeah, but I also think the question refers to actually really when you just get the saturated material, for example, from the grower.
Yeah.
What is then the P concentration as compared to, so when you have wet material as compared to the dried material, because the follow-up question is then if this P, so the lower amount when you have fresh material, was taken into account and the interpretation of your sorption desorption experiments and the SEM EDX data.
Yeah. Dus we know now. This was from one experiment, from the completely distracted granule. We had 1.5% in mass of P. What we can desorb from that granule was only 40%. 40%, and afterwards we didn't do any analysis on the concentration of the P that maybe is still on the material, so that we don't know.
Okay. Yeah. Then another question is, have you done already any experiments with the regenerated material? Can it absorb the same amount of P as before?
Certainly not, I suppose, but we will start up our columns and do the experiments. And it is our intention to do different cycles of adsorption and desorption, but we don't have the results at the moment.
Okay.
But I think the adsorption will be less in the second cycle.
Yeah, I also think it will be. Yeah.
And I think the result will, you will see after a while, the breakthrough time will be faster and faster, and you have to do at a regular basis your desorption. What we want to do is filter, adsorb during the week, and then take the weekend to desorb and start again with adsorption during the week. That's the next experiment that we will do.
Yeah. And then another question, do you think that the bonds are different after longer times, and could that influence the desorption?
Yeah, there are two things. We now know that the phosphorus will migrate towards the core of the granule when you have longer contact times. That we know for sure. And when the adsorption is only at the surface of the granule, we suppose it's a physical bonding. And when you have longer contact times, it will be more difficult to desorb it from the granule. That we know for sure.
Yeah, we know it. We saw it indeed. Okay, these were the questions for your part of the webinar.
Yep.
Then I want
have to.
Yeah, you can stop sharing your screen, and we will proceed now with the last speaker of today. This is Stefan from Rostock University. Stefan, you can start sharing your screen, and he will tell us some more about his modeling work on pea removal. Thank you, Stefan. Go ahead.
Yes. Hello, everybody. I hope you can hear me loud and clear.
Yes, we can.
My name is Stefan Koch. I work at the University of Rostock in the soil physics working group that is led by Professor Bernd Lennartz. And together with my colleague Els, we are working in the field of phosphorus removal modeling within the NuReDrain framework. Yes, as we get deeper into the field of phosphorus removal from drainage water, we like to estimate the effect of the installation of multiple pea filters in the field to the overall nutrient loads of the entire catchment. So that's what we did in our work package. And as we all know, eutrophication is one of the major threats to coastal ecosystems in Europe and worldwide. Harmful algae blooms caused by elevated phosphorus and nitrogen loads may cause deoxygenation of water bodies, not only in the deep regions of ocean waters, but also in coastal regions. And the main reason for this are nitrogen and phosphorus loads from agriculture. Yes, and on these photographs, I'll check my laser pointer. On these photographs, you can see the effect of these algae blooms in the North Sea region and other regions in the world, like the Great Lakes in the US. And of course, there are many studies available regarding the eutrophication potential in the North Sea. As you can see here, we have problem areas near coast at the Benelux states. So in Belgium, we have the potential to reduce phosphorus loads from agriculture. And that's what we try to achieve in our project, of course. First, I'd like to introduce you to the Camelbak Watershed, our study site of interest for the pre-reduction modeling. The Camelbak Watershed is a Belgian watershed in the Flemish part of Belgium. It is approximately 74 square kilometers big and situated in Western Belgium, as you can see here. It is predominantly agriculturally used with a total area of 60 square kilometers, which is approximately 83% of the whole watershed. So yeah, as you can see, it's really agriculturally used. And hence we got the large export rates of phosphorus from these watershed. It is a heavily tile-drained watershed that is dominated by loamy soils, and alluvial soils stream near. So as you can see here, near the streams, we got alluvial soils, and the rest of the watershed is basically dominated by loamy soils. Approximately 70 to 85% of the catchment is drained area, so tile drained area. But we have to emphasize that the estimation of drained areas is a challenging task because it's not well documented. So it's just a proximity value, I'd say. So the total area of drained areas is always a rough estimate in the description of watersheds. Here you can see the concentrations of nitrogen and phosphorus in the watershed. And as you can see, in terms of the target values of the Water Framework Directive from the European Union, the loads of nitrogen do not exceed the target values of 50 milligrams per liter at all, but the phosphorus concentrations by far exceed the target values of 0.15 milligrams per liter. And so we have a very, very large reduction potential for phosphorus in the waters of the Camelbak Watershed. Yeah. The modeling we did was done using the soil and water assessment tool, which is called the SWOT model. And we used it to model stream flow and the phosphorus loads in the tile drains. The SWOT model is a physically based eco-hydrological model with a very sophisticated tile drainage routine, which makes it particularly suitable for our watershed of interest. The fundamental spatial resolution of the model is the Hydrological Response Unit, HRU. This is a linear combination of a digital elevation model, a soil map, and a map of land use. The temporal resolution can be chosen according to the temporal resolution of your input data, which can vary between hourly to yearly values. Here I like to visualize the setup of the model. The first input is a digital elevation model which delineates the watershed boundaries. Then you add the soil data and a map of the land use in the watershed, which together form the so-called HRU. Together with the weather data in the target temporal resolution form the basic model input. And we can, of course, choose the variables of interest to calibrate the model too. So this can be discharge and, of course, nutrient, sediment, or contaminant data. If we talk about modeling, we need to know how to evaluate the quality of a hydrological model. And there are different approaches how to evaluate this, and we chose to consider the Nash-Sutcliffe efficiency, NSE, as the evaluation index. The range of the NSE is from -infinity to 1. 1 represents a perfect model fit, and values above 0.5 are considered as good, and above 0.75 as very good. On these pictures, you can see different values of the NSE. The NSE of 1 is obviously a perfect model fit. So the red and the blue line perfectly fit each other, which means a perfect representation of the real flow conditions by the model. An NSE of 0 means that the mean value of the discharge is an equally good representation of the flow as the output of the model. And negative NSEs mean that the model has no benefit in describing the discharge patterns that were measured. So a negative NSE means we don't even need the model to describe our discharge. But we have to emphasize that the consideration of those indexes like the Nash-Sutcliffe efficiency is not only suitable for the evaluation of models. You also always need to consider flow components and general behavior of the model and the parameterization. So you need, let's say, like special knowledge to evaluate the model quality. Now I'd like to present the first results of our modeling approach. And here you can see the calibration results of our modeling period from 2010 to 2015. You see here monthly discharge values. The observed values are shown in blue lines, and the modeled results are the red lines. As you can see, we have a quite good model fit with an NSE of 0.58. You see that the peak flow events are fit quite well, and that at some points we don't fit the discharge events so well. The same is for the DRP loads, so the dissolved reactive phosphorus in the stream water. As you can see here, some peak events are show a really good fit, and some do not. We could achieve a Nash-Sutcliffe efficiency of 0.66. And of course, there are other ways to interpret the model output, which you can see here. Here you can see the sum curves of the discharge and scatter plots of observed versus modeled values. And as you can see, the overall sums of discharge and DRP loads were fit quite well, with a slight underestimation. But however, the scatter plots show that we don't have a constant under or overestimation by the model, which is a pretty good indicator for the model quality. But however, as I told earlier, it is not sufficient to interpret the model results by those mathematical values only. That's why we had to consider the flow components as well. And as I said in the beginning, the Camelbak Watershed is heavily tile drained, and that's why we wanted to achieve high amounts of tile drainage flow in the model output. And as you can see here, during peak flow events, we got really high amounts of tile drainage flow, which is here shown as red lines. We have a constant base flow, which is shown in purple, and only slight peaks of surface runoff in this lowland watershed. Approximately 30% of the total flow origin from tile drainage flow, which is exactly what we wanted to achieve. So if we get back to the NSEs, the NSE of 0.58 might be considered as good, not as very good, but these modeling results with high amounts of tile drainage flow are really what we wanted to achieve. So knowing that the model performed pretty well in terms of the distribution of flow parameters, we were able to implement different scenarios of P-filter techniques. And what we did was we took the P-filters with iron-coated sand that were presented in the last week's webinar on Friday by Xu et al. Into the model. And these P-filters were applied to selected HRUs, so to some selected hydrological response units. The advantage of these filters are that they are easy to install and they show a high P removal efficiency with 80 to 90% P removal. It is a low-cost installation, and a very, very big advantage is that these filters do not cause any impairment of surface waters at all. So these were implemented into the model input in the following way. You can here see the scenarios where we equipped an area of agricultural land that is tile drained with P filters. So we took 5%, 10%, 15%, 25%, 50%, 75%, and 100% of the agricultural tile drainage area and equipped these with the P filter. These were total areas of 300 to 6,000 hectares, and the number of drainage plots were from 51 to 1,000. This was calculated by the assumption that approximately 6 hectares of agricultural land is drained by one collector drain. The annual costs ranged from 16,000 euros to 300,000 euros between the scenarios. I hope this is quite clear how we applied these scenarios. So what happened when we applied these scenarios to the model output? As you can see here, we have the modeling scenarios from 5 to 100%. And here we have the modeled P load. This is our base model, the observed P load of 10,000 kilograms, and the modeled base scenario, and now the reduction scenarios. And as you can see, between the scenarios, we have a wide range of P reduction potential from 250 kilo to approximately 6,500 kilograms of P reduction, which equals a reduction of 3% in the lowest scenario to 66% in the 100% reduction scenario. For those of you that don't like numbers a lot, we can show this as a graphic, and you can clearly see the effect of the P filters in the different scenarios, especially at peak flow events. And the same here in the bar plot. You see that the 100% reduction scenario shows a pretty large P reduction potential for the whole watershed. So if we now conclude, or let's have an outlook, I can't stop emphasizing that these model studies are an estimate. Yeah, so this is not like you apply a filter to the system, and the results we achieved will happen in the real world. It's an estimate. Yeah, it's a scenario, and we need long-term studies on in situ filter techniques that will definitely improve the development and implementation of scenarios in our hydrological models. And we need in situ tests of different filter materials that will help to develop a wider range of scenarios for the P reduction in threatened watersheds. And another thing that our working group will do in the near future is that we will use the same modeling approach for developing N reduction scenarios, because this is, of course, also an important question. So that was our contribution to this webinar, and I thank you for your attention, and I'm looking forward to questions.
Yes, okay, Stefan, thank you for your interesting talk. There is already one question. Leonard is asking if you have any retention retardation in your model, or is all the P that enters the surface water transported to the downstream areas?
Sorry, can you repeat that question for me?
Yeah, so Leonard is asking if you have included retention or retardation in your model, or do you assume that all the P that enters the surface water is also transported to the downstream areas?
Oh, yeah, okay. The model as it works now, or as we applied it, is that all the P that enters the system leaves the system. We modeled the dissolved reactive P from the tile drainage. It is possible to choose another approach where you take the basic model output and apply the filter afterwards. And then you can, of course, implement like retention to the scenarios. So that it is possible, but we didn't do this in the first place.
Okay, thank you. Does anybody else has a question for Stefan? Stefan, yes?
May I ask a follow-up question then?
Of course, go ahead.
Because my question is particularly because if you're calculating reductions, there might be some phosphorus in the system, in the sediments. They will be transported from the sediments, which are more eutrophicated than the new surface water with reduced concentrations. So there might be an extra source of phosphorus from the sediments of the materials that are already in. So that was a question related to your reduction percentages also.
Yeah, that's of course right. You always have like remobilization and desorption from the P-laden sediments. But as we now model, as Bernd mentions, we don't model in-stream processes. We model tile drainage processes.
Yeah, thank you. Yeah, clear.
Okay. Stefan, as you know, we already proposed these nutrient removal technologies to the Flemish government, because we hope that at some locations they would be willing to have them installed. Some of them, I mean, of the governmental organizations, like more the natural approach with the wetlands and so on. So in the future, would it be possible to also model other technologies on the same catchment to see what the contribution of other technologies could be, or if, for example, a combination of different technologies at different locations would be more ideal in terms of economics and nutrient removal?
Yeah, that's of course possible. If you once set up the model and you got good model results for the base model, it's clearly possible to implement suitable scenarios for whatever filter technique you want to apply. Yeah.
Okay. Okay. Does anybody else has a question for Stefan? Ben is mentioning that wetlands would change the water balance. It's true, yeah. Then would retain some
of
water.
Course,
more.
and the proportion of wetlands in the Camelbak Watershed is pretty low.
Mm-hmm.
So.
And can you derive from your model at where are the hotspots and where we should ideally first of all install these filters?
That's a tough question. The basis of our model is, as I mentioned, the hydrological response unit. And if we have a look at the results, we can probably see where are potential hotspots. But again, it's a model.
Yeah, it's an estimation.
It's an estimation, and it's not the real world.
Yeah. Okay. But it's a starting point. Eh?
Yeah.
Yeah. Okay. Okay. Thank you. You can now. Oh, yeah, you stopped already sharing your screen. Then I will share my screen again just to have the concluding remarks. Oh, sorry, it goes. Yeah, okay, but let me already proceed. So first of all, I want to thank all the speakers for the nice presentations. Okay, we come to the end of the this webinar. I just want to highlight that next week we have the last of our 3 webinars, and then we will focus on removal technologies for nitrogen from agricultural waters. So if you would like to subscribe also for this webinar, you can find the subscription link on our website. And so with that, I want to conclude this webinar for today. I want to thank the project partners, and I want to thank our funders, being the Interreg North Sea Region Program, and then also the province of Antwerp, East Flanders and West Flanders for the Belgian cases. So thank you very much for being present, and you will receive the video and the handouts afterwards. Thank you. Bye-bye.
Thank you.
Bye.
Bye. Thank you.
Bye.